Hello everyone, welcome to the video as promised. So I put in some effort to make this, it helped me study. What can I say except you're welcome.
What can I say except you're welcome?
And I know you're probably, what you're probably thinking of me as you watch this video. So, time series theory by me.
I am the chosen one. Somebody had to do it.
Okay. So the nature of time series data. So it is the temporal ordering of observations that you cannot arbitrarily reorder it. So if you have data on the GDP in 2008, 2009, 2010, year t equals 0, t equals 1, t equals 2, you can't just reorder them, right? So for example, if you're looking at GDP, the great financial crash happens before 2010. So you can't just swap around those numbers, it won't make sense. A few typical features. Firstly, serial correlation or autocorrelation. So the value of a variable or the error term at time t is correlated with its own past values. So what I would say is, if you're in a test and they ask you for what serial correlation means, just remember to mention that it could refer to either the value of a variable or the value of an error term. So all this means is that if you think of something like GDP growth or GDP, the value in 2010 is probably quite correlated to the value in 2009 because it's probably not much less than the value in 2009, right? And like stuff that happened in 2009 affects stuff that happens in 2010. So if the GDP is 100 billion in 2024, it's probably not going to be zero in 2025. It'll either be maybe 95 billion or 105 billion. So there is correlation, right? And interpreting the errors, we'll get to that when we do the questions. But yeah, that's serial correlation, autocorrelation. We also assume, or we know, that we don't have independent observations. So usually when you're doing sampling data or cross-sectional data, you're going to sample, let's say you want to look at the marks of students at UCT. You're going to sample across 1,000 students, and then maybe you want to see how are marks determined by study hours, race, economic background, etc. Right? But you assume that your samples are independent. With time series, right? So let's say a time series of GDP, a time series of the marks that students in Eco 3021S get. These are not independent observations because the observations depend on each other, right? The mark of Eco 3021S in 2026 is not going to be that different from the mark this year, or the GDP in next year cannot be too different from this year. So it is dependent on the value this year, right? And so if the value this year is a certain value, that affects what the possible outcomes could be for the next year, right? There are also, we can say time series is essentially a sequence of random variables, right? So what we mean by this is, t is the year. So t equals 1, obviously we can just say what the year is. The random variable is the value of the thing that we're measuring in a given year. So if t equals 1 is 2008, then the random variable is the, let's say GDP in 2008, right? And then GDP in 2009 and so on. Those are random variables. But there is a randomness in terms of them. We can't ever accurately predict GDP. And that doesn't come from the sample, doesn't come from sampling, right? It comes from the fact that, there's inherent randomness in a time series like this. So when you say a sample, it is the one realized path of the time series out of the many possible paths of the stochastic process it could have taken. So we'll define stochastic process here. So, just think, the GDP in 2026, we don't know it. It's not because of our sampling data. It's because there are many different possibilities, many different paths of the stochastic process it could take on. We'll define a stochastic process a bit better or more precisely according to what the UCT people want. But just generally, it's a system or phenomenon that evolves over time according to probabilistic rules. So its future states are influenced by random variables and are not entirely predictable. So what does this time series analysis focus on? It focuses on modeling the dependency of a variable on its own past and on the present and past values of other variables. So for example, we can model the dependency of GDP in 2010 based off of the value of GDP in 2009, 2008, 2007, 2006, and so on, right? So for example, if we see GDP is increasing every single year, that probably means GDP is going to increase in the given year that we're testing. So there's dependency of this variable and its past. But we can also say, GDP in this year how is it affected by the unemployment rate? How is it affected by inflation? How is it affected by government investment, right? So we can model the dependency of a variable we're measuring, GDP, on, let's say, the present value of another random variable, inflation, or the present value of another variable, unemployment, right? Or the past values, so the past values of unemployment, the past values of inflation, etc. That's what time series analysis focuses on. So static models. So when you think static, think it stays still, it lays still, it doesn't move, it's just in the current year. So for example, in this model, how is inflation in year 2, right, in year T, right? How is that explained by, we've got the constant, the coefficient of unemployment in the given year, and the error term in the given year, right? So static models, we take the current value of the dependent variable, and we say it's modeled as the result of the current value of the explanatory variables. Okay, and then a word here is, we can say that there is a contemporaneous relationship between inflation and unemployment. So I'll say again, there is a contemporaneous relationship between inflation and unemployment. So what does that mean? Sorry, I just actually used my voice to put that into Google because I actually forgot the definition. Oh my word, okay, if this thing can... So it just means existing or occurring in the same period of time. So contemporaneous relationship is just the relationship at equivalent points in time. So for example, again, this would be a static model, the suicide rate in year T equal to a constant plus a coefficient multiplied by the GDP in year T plus a coefficient multiplied by the unemployment in year T plus an error term, the error term in year T. Then finite distributed lag models, okay? So here we can say that the explanatory variable, right, is allowed to influence the dependent variable in year T with a lag. So for example, the fertility rate in year T is equivalent to a constant, right, plus a coefficient multiplied by the independent explanatory variable, right? And in this instance, that would be a tax exemption for people that have kids, right? And so we assume, let's say this tax exemption was codified into law 2, 3, 4 years ago, so it stays the same every year. So the value of the explanatory variable in this instance, or in this example, is the same in year, T, T minus 1, T minus 2, etc. Let's just assume that, right? Good. So the general form of these things is y in year T equals to alpha naught, that's a constant, plus, what do you call this thing? Let's call it like alpha or whatever. Whatever. That's thingy key, the 0, zt plus thingy key 1, zt minus 1, etc. up to thingy key q, zt minus q, right? The thingy key is our beta coefficients, right? Beta 1, beta 2, beta 3, right? And the zt minus I is the explanatory variable value in a given year, year t minus I, right? So let's think of shocks with the finite distributed lag model. So we would, if you think of transitory or temporary shocks, you would just say, what is the change of the dependent variable in the given year over the change, the change in the dependent variable year to year over the change in, the change in the dependent variable in this year, in the given year, divided by the change in the explanatory variable in year t minus s. That is equal to, let's just call this thing alpha s, right? And so alpha s or alpha 1, if you say, if you take the derivative, similar thing, it's just the marginal effect of the explanatory variable in a given year on the dependent variable, right? And so for example, if if lambda 1 over here is equal to, 0.5 or 1, we would say that the tax exemption, whatever it is, let's say 5,000 Rand, right? A 1 unit increase in the tax exemption has a 5,000 Rand increase in our dependent variable, which is the fertility rate, for example. And then if we do, for example, a permanent shock, so if you say the change in the dependent variable in a given year over the change in zt minus s all the way, and you add them all up, right, you get the sum of the coefficients, and that just gives you the long run cumulative effect of the shock on the dependent variable, right? So now the theory of the finite sample properties of OLS under classical assumptions. So firstly, first assumption, it's linear in its parameters, easy to remember. So you can write it out in the form yt equals beta naught plus beta 1, xt1 plus beta k xtk plus mu t, right? Then the second assumption is that there's no perfect collinearity, right? So that means that, you know, the sample, and therefore in the underlying time series, there are no independent variables, right, which are constant or that are a perfect linear combination of others. So you can't have, for example, GDP in year t and another one that's like 4 times GDP in year t, right? That's not going to make sense, right? Or it's going to violate the assumption of no perfect collinearity. And then in the third assumption is the zero conditional mean, right? So we would say that the expected value of the error term in year t, given big X, we'll get into what that means just now, that is equal to 0 for all values of t, right? And so what that means is that the mean value of all our unobserved factors are uncorrelated to the explanatory variables in all periods, right? So what do I mean by this big X? I basically mean, right, this is a vector, right? It has a tth row and a kth column. So it's the matrix of all explanatory variables in all time, right? So for example, x 1, 1, x 1, 2, x 1, 3, that is the first explanatory variable in a given year, right? And then x, you know, down to x, what is this, nk, that would be the explanatory variable, a given explanatory variable over all time. Sorry, I'm getting the things a bit confused, but basically that big X just means for all explanatory variables over all of time, right? And when we say exogeneity, we mean outside of our model. So the assumption that we have here that we use, that is the third assumption of zero conditional mean, is strict exogeneity. So strict exogeneity means that the expected value of our error term for all explanatory variables over all time, right, is strict exogeneity, right? Now, if we have the first, second, and third assumptions satisfied, we have an unbiased estimate of our coefficient, right? So the expected value of the, you know, whatever our predict or our expected coefficient is equal to the true population parameter coefficient, right? For, you know, j equals 0, 1, 2, 3k, right? The fourth assumption is on homoscedasticity, right? So you guys should be sick of hearing that from the previous section, but it's basically to say that for all our explanatory variables over, you know, all time, the variance of the error term is independent of x. So the variance of the error term given all values of x is just still equal to the variance of the error term, which is just equal to a constant. I think that's sigma squared, or I'm forgetting all my Greek letters, for t equals 1, 2 until n, right? So the volatility of our errors are not related to our explanatory variables of any period, right? So the GDP being high or low or anything like that, that is not correlated to any of the error terms that we're not, you know, anything that we're not measuring, right? There's no correlation between the two. So the error terms doesn't change when you change the value of the explanatory variable, and the variance of the error terms don't change when you change the values of the explanatory variables, right? And then the fifth assumption is that we have no serial correlation, right? So that means the correlation of the error term in year t and the error term in year s, which is just some other year, right? So any year in terms of, you know, any year and another year, right? The correlation between the error term in year t and the error term in year s given x is equal to 0. So that just means that there's no error memory. So for example, knowing the error in 2008 does not help you to know the error in any of the other years, right? So there's no correlation between the errors. We can't say, oh, if the correlation in 2000, you know, if the error term in 2010 is 100, that means that the error term in 2015 is, oh, some other thing, because there's this, you know, correlation or linear relationship between them. No, you know, knowing the error term in a given year should not help you mathematically or statistically know the error term in any other year, right? That also means that, you know, your shocks are unrelated. So, you know, shocks relate to an error term. You know, something shocking happens, obviously the model is gonna not predict it very well. because it goes against what we've seen before. But there being a shock in 2008 shouldn't predict there being a shock in 2010, right? So a change in the error term in 2008 should not be correlated to a change in the error term in 2021, which is like when COVID happened. So now, if we have the first to the fifth assumption satisfied, then we know, right, that the variance of our beta coefficients, the expected values, given x is equal to this whole thing. So sigma squared over SST times 1 minus r squared of j for j equals 1 to k. I didn't add the interpretation here because even in the slides, they seem to admit that it's pretty confusing. So I won't get into that, but maybe that's useful for you to know, just to like have it in front of you. I didn't take the time to understand what exactly it means. And then also, this is more important, when you have the first 5 of these assumptions satisfied, you have an unbiased estimation of the error term, right? So the expected value of the variance is equal to the true population variance. So that means that, we have a minimum variance of all unbiased estimators of regression coefficient. So the regression we're using, the OLS one, has minimum variance of all unbiased estimators, right? So that's nice. So that's in terms of your, we have, I guess you can say, efficient estimators, right? It's the lowest variance possible. And then the sixth assumption is that of normality, right? So what does this mean? It means that our error terms are distributed normally with a mean of 0 and a constant variance, right? And that they are independent of the explanatory variables, right? So if they're normally distributed, it means that they can't have a weird shape based off of whatever like is happening with our explanatory variables. So that implies as well that we've satisfied the third to the fifth assumptions as well, right? So the third to the fifth. So we've satisfied that there's no correlation, that there is homoscedasticity, no heteroscedasticity, and that we have strict exogeneity in terms of our assumption of the zero conditional mean. Okay, so if all of that is satisfied, then if we have normality, that assumes we've satisfied those 3 other assumptions as well. So those are the six assumptions we make when we do the time series analysis using OLS. So now let's quickly look at how to use and interpret dummy explanatory variables in time series. So let's look at, for example, the fertility rate in year T is explained by a constant, right? Plus, let's say, a tax exemption in the current year, plus the fertility rate during World War II, plus the years in which the contraceptive pill was available, plus an error term. So, for example, if World War II has a coefficient of negative 24.25, so we can say that, holding all else constant, the fertility rate was 24.25 units or whatever less in the years 1939 to 1945. But that applies only in those years. But if we look at the effect of the contraceptive pill in year T, right, we would basically say, what is the effect of having the contraceptive pill available on today's fertility rate? Or obviously, if all of a sudden the contraceptive pill got banned or wasn't available, didn't exist anymore, then we would, I guess, switch the dummy variable off you can think of. But we can say that if the coefficient for pill is negative 31.59, so we say that the level in whatever year, in the current year, of the fertility rate is 31.59 units lower because of the existence of the pill. And so it can think of these dummy variables of things that you can switch on and off. So the pill variable has been on, quote unquote, since 1963, but the World War II dummy variable was only on between 1939 and 1945. So if you were doing a time series analysis of fertility in 1939, 40, 41, 42, 43, 45, 44, 45, then you would add in the World War II thingy key to be like, oh, this is the effect of there being a war happening on the fertility rate. But in 1946, 47, 48, you would remove that because World War II is no longer a thing that can explain the fertility rate, right? And then let's quickly go here. So when we go to the second part, the other slides 1 to 9 of still on time series, but in week 9. So when we have time series with trends, right, those trends can either be linear or exponential. So with a linear trend, you think of constant growth. So think of, for example, if you have parents who love you, Some parents love you, but they don't give you money, which I'm like, what's the point? But if you have parents that really love you and they deposit money into your savings account, let's say 1,000 Rand every year, right? Not that much, but maybe they're not stacking paper like that, but they give you 1,000 Rand every year, right? That's a time series. So year 1, year 2, year 3, year 4, there's a constant increase by 1,000 Rand. When you think of an exponential model, or I guess technically kind of like a logarithmic model, basically, you have percentage growth. So if you think about the GDP growth in a given year, we model it as a percentage of year t minus 1, right? So if you go from 2010 to 2011 to 2012, and we know that there's probably constant GDP growth, but not in terms of a fixed value being added each year, but as a percentage in growth. So if it's growing 10% each year, you'll go from 10 to 11 billion and from 11 to 12.1 billion, right? So not by a fixed value of a billion, right? And then let's define a trend. So a trend has a few components. It is a long-term, systematic, persistent movement in one direction. So I've given you guys an example for you to remember. So let's say on the y-axis we have hose, and on the x-axis we have time. So this is now for me. So we can see that there's a persistent upward trend for me, that over time I get more hose, right? So that there is a trend because there is a long-term, systematic, persistent movement in one direction up, right? So obviously by hose, I mean the gardening tools that I'm purchasing for my landscaping business, right? But here there's this huge persistent upwards trend. You'd be like, oh my word, Christian is getting so many hose over time, and there's this clear upward trend. In year t equals 2, he's got 5 hose. In year t equals 10, he's got like 100 hose. It's just going up and up. So there's a constant upwards direction. There's a similar direction, and it's constant every single year. And so when you're modeling a linear time trend, you can use this, sort of standard form. So yt equals alpha naught plus alpha 1t plus error term in year t, right? So alpha naught is our constant, alpha 1, and this is not alpha 1 in year t, okay? This is alpha 1 times t plus the error term in year t. So if you take the expected value, right, of a change in yt. So for example, what is the expected change in our dependent variable? Let's say yt minus 1. So for example, with the depositing money in your account example, if in 2025 you had 2,000 Rand and in 2024 you had 1,000 Rand, right? 2,000 minus 1,000 gives you lambda 1, gives you 1,000. So lambda 1 here is just the constant growth in the time series, right? And so here's a little bit of math explaining how that would work. So if we take yt minus 1, we would have alpha naught plus alpha 1 times t minus 1 plus the error term in year t minus 1. If we get a difference, so subtract yt minus 1, right? You'll end up with lambda 1 plus the error term in the current year minus the error term in the previous year. And when you take the expected value of all that, you're just left with lambda 1. So that is your constant growth over time. So think of the money being deposited. So you're adding 100, you're adding 100, you're adding 100, right? Your lambda is just, if your yt is 2013, your yt minus 1 is 2012, 400 minus 300 is 100. So your lambda 1 is just the value of the constant growth in your linear model. Now, in Stata, if you want to do something like this, how do you do it? So you say gen time equals underscore n, and then you use this notation, regress y x time, and with obviously a space in between each. So just quickly, that's how you do it in Stata. And then when you model an exponential time trend, so they say in the memo they say log. Now the problem is, remember, log can have any base, right? The log which they use is a log with the base e, which is Euler's number. So actually that's ln, and most calculators have that. So I've written here ln instead of log, but just know it means log. I'm just being more accurate than them. So ln of yt equals lambda 0 plus lambda 1t plus error term t. So it looks exactly the same as the previous one, except now we've logged the yt. And now when we say the expected value of a change in log t is equal to lambda 1, what is that? That's our constant percentage growth, but it's just note that it's an approximation. It's not an exact percentage growth, but it's very close to what the real constant percentage change is, right? So when you exponentiate this, right? Oh, just quickly on an example. So if you go 2020, 2021, 2022, if we're growing by 10% each year, right? So 100, 210, 221. So probably with stuff like economic data, with GDP or whatever, anything where the especially the original value stays the same and grows by some percentage, we're going to use an exponential model. It's literally the linear model. We're just logging our y of t. And then when you exponentiate it, you just say y near t equals, the exponentiated value of lambda 0 plus lambda 1t plus e, the error term t, right? How do you interpret that? Well, then let's say, for example, lambda 1 is equal to 1.5, right? You would just say that it is the multiplicative effect of lambda on y. So a 1 unit increase, a 1 unit change year to year, right, results in a 1.1 times yt change in yt. So that is to say, if lambda, once you've exponentiated it, so e to the power 1.1, for example, right, it just means that you are multiplying your dependent variable by 1.1, right? So that's how you interpret it. It's a multiplicative effect. Okay. Whew. Okay. So in general, we prefer simple trends because we want to capture the broad movements in the dependent variable. We don't want to be too complicated about it. We want a pretty simple model that looks like this. And then now, why is it bad to regress on trending variables? So why is it bad to regress trending variables on another? We get a spurious relationship. So note, this is not like a relationship of people that go to Spur and have a test for life. A spurious relationship is false, misleading, or fake. You could even say someone is like, your friend is spurious, like she's a fake ass bitch, she's a very spurious friend, right? Like my boyfriend cheated on me with her, right? That's a spurious friend. So similarly, when statistics, right, you can have misleading relationships because you're just saying, oh, well, this thing has an upwards trend, this thing has an upwards trend, so this thing is causing that thing. So for example, since 1960, there's been an increase in feminism and there's also been an increase in global warming. So now what are you going to do? You're going to say, oh, women and activists, feminist activists are causing climate change. No, that's stupid, right? So I've given you guys another bit of an explicit model here. So, and I will define exactly what each component means just a bit later, but just bear with me for now. So the expected value, so expected log of bitches equals negative 0.550, your constant, plus 1.241 log, your marks in Eco 3021S. And then this is expected, so we don't have the error term, right? So now we will say, okay, so is increasing your marks associated with getting more bitches, right? And so according to this model, if you take the coefficient divided by the standard error, 1.241 divided by 0.382, you'll get a t-value that shows you this is statistically significant, right? But really, what's happening here is that there's a trend in both, right? There's a trend in the marks that that people are getting, and there's a trend in the bitches that people are getting, but the two aren't necessarily related, right? And so what I mean here by bitches is female dogs. Obviously, the amount of female dogs being adopted over time is going up, right? However, what am I going to do here? Oh, okay. So this thing moved things around a little bit. I'm sorry. But if we include 0.0098t, that is a trend term, right? So that basically takes out of the error term the information we have about the trend and we put it in it. So now we say, what is the relationship between marks and the amount of bitches someone has if we control for the general upwards trend? And what now happens is that coefficient for the explanatory variable of marks is now no longer statistically significant, right? So they love asking a question about this. So just mention the spurious relationship, the fact that both have a trend. You remove the trend from the error term, you include it. So you control, you say, you say, what is the effect of marks on getting bitches controlled for the trend term? And then you'll see, oh, it's not statistically significant. So that means that the previous one, where we didn't detrend it or we didn't include a trended term, was giving us a spurious relationship, right? Okay, so you include it if any variable dependent or independent displays trending behavior, right? And so also know when you include time trend, you are detrending the data, right? And we do that so we avoid falsely attributing trends to causal relationships, right? And then just some extra theory that I realized I didn't include. So firstly, what is long run propensity? So let's say you have this model. So beta naught plus beta 1 zt plus beta 2 zt minus 1 on and on plus the error term in year t. So what is that? So we're saying the coefficients is the effect the explanatory variable in year t or year t minus 1, etc. had on the value of the dependent variable in year t, right? So the long run propensity, how do you calculate that? You just sum up all your coefficients. So you sum up beta I. I think I made a mistake here. It is not, you don't sum up the constant. You sum up from beta 1 up to beta 4. So please note, you don't sum up the constant. That was a small mistake by me. How do you interpret it? It is the cumulative effect of the current explanatory variable and its past values on the dependent variable in the current year. So this shows us the importance of the immediate or contemporaneous impact. So beta 1 would be the contemporaneous or immediate impact, the impact that the explanatory variable has in the current year that we're looking at the dependent variable for. It also shows us delayed impact. So how does the value of the explanatory variable, 4 years back, how does that affect the dependent variable in the current year, right? And so we're saying for every 1 unit increase in the explanatory variable, the dependent variable is expected to increase by the long run propensity, right? Which is the summation of beta I, not I equals 0 to n, I equals 1 to n. So for example, look at something like this. So if we have sales in year t, and we have this model. So the constant is 50 plus 0.4 expenditure on advertising in year t plus 0.3 expenditure on advertising in year t minus 1 plus 0.2 expenditure on advertising in year t minus 2 plus an error term. What is our LRP? So we sum up 0.4, you see, not the constant. So 0.4 plus 0.3 plus 0.2 is 0.9. But the way we could interpret that is, I think this is now, the advertising is given, the advertising is in thousands of rand. Right, so a permanent increase of $100 or of $1,000, in advertising budget leads to a total long-run increase in sales of. Let's just add that. It's to a total long-run increase in sales of $900. Okay. Then quickly, Stater and Lags, they have asked some questions on this. I don't know if they will. So let's say you have this function. So y of t equals beta naught plus beta 1 xt plus beta 2 xt minus 1 plus beta 3 xt minus 2 plus, let's add this here, t minus 2 plus beta 4 yt minus 1. So that one's a bit tricky. But that beta 4 yt minus 1 is just saying, how does the previous year's dependent variable value affect the current year's dependent variable? That is what beta 4 tells us. But yeah, how do you regress that? So you say y space x space l dot x space l2 dot x space l dot y. So when you say l dot x, that's you're lagging because of the xt minus 1. So that's just a lag of 1. When you say l2 dot x, that is xt minus 2. So that is a lag of 2. And then when you say l dot y, that's just saying we know that there's a lag of 1 on the y variable. Okay, and then a lag distribution, right? What is that? So it is how past values of the explanatory variables xt affect yt, right? So let's take this regression that we have here, and they say form the lag distribution. So I think this is slightly incorrect compared to what they want, but it is just you have to put together all your coefficients, right? So let's say 0.8, 0.5, 0.3, 0.4, let's say. So for beta 1, beta 2, beta 3, beta 4, right? That would be your lag distribution. So it's not necessarily that you're like summing it up. It's not your long run propensity. It's just saying that in each, your lag distribution is for each year, what is the value, right? So you could also, I believe, write it as, let's say t equals 1, it's actually crazy how this thing takes time to just go back on something like that. Look at how retarded the thing is. Okay, t equals 1, t equals 2, t equals 3, right? And then what's the coefficient associated with that? 0.8, 0.5, 0.3, and so on. So that could be your lag distribution, for example, right? And so if we think of a finite distributed lag, right? We think of the impact propensity versus the long run propensity, right? The impact propensity is just what is the impact of the explanatory variable in the current year that we're looking at on the dependent variable in the current year. And our long run propensity is what is the impact of that's what we did our LRP, that what is the impact of the explanatory variables throughout time on our dependent variable in the current year. And then again, just quickly a note on serial correlation. So it is just to say, are the error terms correlated with themselves over time? Are the explanatory values correlated with themselves over time, right? And so if you have correlation, so if the covariance or the correlation between error term in year t and error term in year t minus s, or error term in year s, where t is not equal to s, if that is not equal to 0, so you have some correlation, some covariance, right? The OLS, you still have unbiased estimators, but they're not the most efficient. You don't have minimum variance, right? And then when we think of time series versus cross-sectional data, so cross-sectional data, that's just observations collected at a specific point in time with no dimension, right, across different entities. So if you look at if we collected 2024 Eco 3021 S marks for test 2, it would be collected at a specific point in time across multiple entities being multiple students, but there's no time dimension for that, right? Or something like the number of hose, let's say you modeled something on cross-sectional data, right? So you took a bunch of people, so y is your dependent variable, you say the number of hose they have, gardening equipment, is equal to a constant plus a coefficient times the mark they get for this course plus an error term, right? So obviously here, for example, what we're used to seeing is your coefficient beta 1 would be positive, very statistically significant, so there's a huge correlation between the mark you get and the number of hose you have. And the thing is here with a time series is that it's temporal, right? So it's we have random variables that tell us the value in year t, right? And then infinite distributed lag model. Sorry, I actually almost broke my tablet the amount of times this thing was glitching and irritating me with random shit that it was doing. But anyway, infinite distributed lag models, right? So if you have the dependent variable year t as a regression or as a function of the the explanatory variable in year t minus 1, minus 2, minus 2, minus 3, minus 4, minus 5, and just on and on and on with no end, right? That is an infinite distributed lag model. Whereas remember with our finite distributed lag model, we would lag it up to a specific point, so up to 4 years, up to lag 1, 2, 3, 4, 5, 6, whatever it may be. But an infinite distributed lag model is just we take infinite lags, which in practice technically isn't possible because we obviously don't have infinite amounts of data. But what you would do is you would just, there's a decaying factor or whatever, but we don't need to know that. That's not super important. Okay, so this has covered the theory component of time series, and if you've paid attention here, then when we do the questions, they should be pretty simple. So I'm gonna cut to doing the theory questions now. Do the questions. So this is some stuff that was compiled by me. This is a picture of me for those of you who are wondering what I look like. It's from the internet. So let's get into the questions. So the way I've formatted this is it's just a slideshow. I've just copy and pasted the questions either from the memo or from what I found on the internet, or like using AI or whatever. So define a stochastic process. So it is a collection of random variables indexed by time. So this is a little bit different to the definition that I gave earlier. This one is the one you should use. So a stochastic process is a collection of random variables indexed by time. It describes how a variable or a set of variable changes randomly over time. Cool, nothing crazy. What is a stochastic process in time series analysis, and what is its significance? So a stochastic process in time series analysis is a model that represents a sequence of random variables over time. There's the whole thing. So it incorporates both deterministic trends and random fluctuations. Its significance lies in its ability to capture the inherent randomness and variability in data, enabling more accurate forecasting and analysis. So it's a sequence of random variables over time with incorporating trends and random fluctuations. So it's significant because it captures inherent randomness and it enables accurate forecasting and analysis. So what is meant by trend, cycle, and seasonality? So I'll just focus on the trend component. So a trend is just a long upward or downward movement in the data. So it's a bit simpler than the definition I gave, but yeah, a long-term upward or downward movement in the data. And then you can read the answers for cycle and seasonality if you want to. State 3 reasons why it is important to understand these components. So it's crucial for correctly specifying the model and accurately interpreting relationships between variables and improving your forecast accuracy. So especially accurately interpreting relationships between variables, because if there's a trend, for example, and you don't include, or you don't understand this, you don't include this in your time series when it's present, especially between a dependent and explanatory variable that both have a similar trend, then you might have a spurious relationship or a misleading relationship where none actually exists. So you're going to infer causality when you shouldn't infer causality, when causality doesn't actually exist. So again, for example, if you say, for example, during the summer, the amount of ice creams that get sold and the amount of people that die of drownings. Ice creams don't cause drownings and drownings don't cause people to buy ice cream. It's just that both have an upward trend during the summer. So compare and contrast a static model, we discussed that, and an infinite distributed lag model in econometrics. So what we've said is a static model examines the relationship with independent variables and a dependent variable at a single point in time, right? So the relationship is assumed to be instantaneous, right? And so we assume that the effect of an independent variable in a static model, effect of an independent variable on the dependent variable is immediate and it does not persist over time, right? And so an infinite distributed lag model accounts for the effects of independent variables on the dependent variables over multiple time periods, right? So it includes multiple lagged values of the independent variable, allowing it to capture the dynamic relationship and the cumulative effect of past values on the current value of the dependent variable, right? And so also this model assumes that the effect of an independent variable can persist over time and includes lags of the independent variable in the model. Okay. So what is the equation for a static time series that analyzes the impact of temperature and rainfall on crop yield? So it would be yt equals beta naught plus beta 1, t of t in year t plus beta 2, r in year t plus error term t. And so again, obviously here at static model, you don't have any lagged variables, right? And so if we have a finite distributed lag model up to 2 lags, we're going to say, our coefficients of unemployment or whatever in year t minus 1, that's lag 1, and in year t minus 2, that's lag 2. And then we're going to add our error term, right? Cool. Now, how would you formulate the stator command to estimate the equation beta naught plus beta 1 x in year t plus beta 2 x in year t minus 1 plus beta 3 x in year t minus 2 plus beta 4 y in year t minus 1 plus the error term t, right? So we're going to say regress yx l dot x for the lag 1, l dot dot x for lag 1, L2 dot x for lag 2, and L dot y for beta for y in year t minus 1. So lag 1 for y plus the error term. Okay. So now, suppose you have the following two variable time series regression model. So in year t, the value of the dependent variable in year t is explained by, was equal to the constant plus beta 1 times x in year t plus error term t. So y is obviously the dependent variable, so if you know the error term is correlated with the past value of the explanatory variable, xt minus 1, what potential issue what might you be facing with the error term, right? So firstly, if it's correlated with past values, this indicates a potential issue of omitted variable bias, or more obviously autocorrelation in the error term, right? Which we said is there's zero conditional mean of the error term. There's also zero conditional variance of the error term as part of our OLS assumption. So we're violating those assumptions, right? So how would you modify the model to account for this relationship? So you could modify the model to include the lagged values of the explanatory variable as an additional regressor, right? So this approach helps to capture the effect of the explanatory variable in year t minus 1 and adjust the correlation between the error term and xt minus 1. So that's what you would do if you saw that the error term is correlated specifically with the past value of the explanatory variable xt minus 1. And then you would just add that in. So beta 2 times xt minus 1 plus error term, you'd add that in to the model. Okay, so given this equation, how should beta 1 be interpreted? So very simply, so that's the immediate impact of a 1 unit change in the independent variable z of t on the dependent variable y of t, holding all other factors constant. And then now, using a variable such as the sales of a commodity, intuitively explain what serial correlation is in the context of time series data, right? And so there's a definition, what is it? So there's a relationship between a variable's current value and its past value. So past sales values influence the future sales values. If I sold 1,000 units of diamonds in the next year, that whatever that year's diamond sales is, or whatever, is probably influenced by the previous year's sales, probably similar or around about 1,000. Okay, so now they say for 2.14, assume we have this time series, express the cumulative effect or the long run propensity. So we discussed long run propensity. You just sum up beta 1 and beta 2. So if there were more beta 1s, beta 2, if there's beta 1, beta 2, beta 3, beta 4, etc., you sum those up, right? And then, the next question that you do exactly that. So what do? You just sum up beta 1, beta 2, beta 3, beta 4. And again, please, not the constant, okay? Cool. And now they say, assuming the value for all these values are that, calculate the long run propensity again. Okay, but more importantly, the interpretation. So you add those up, you get 1.1. So what does this do? I think there's also the question from the slides that he kept hidden from us that was sent on the group. So it indicates that for every 1 unit increase in the independent variable z of t, the dependent variable y of t is expected to increase by 1.1 units in the long run. So this reflects the cumulative effect of the current value of z, the current value of the explanatory variable, and its effects from the past 3 periods on y, or the past however many periods on y, demonstrating the importance of immediate, and delayed impacts in the relationship between z and y. Okay, given this equation, illustrate the lag distribution and analyze how this reflects the largest effect of z on y as well as its influence over time. So, this is how you do the lag distribution. So you've got your coefficient, you've got your lag. So for example, 0.5 has a lag of 0 because that's associated with z in year t, in the current year. 0.3 has a lag of 1 because that's associated with the zt minus 1, right? Lag 1 and so on. So we can see that the largest immediate effect of z on y is the current value, z of t. And we can see that this decays, right? So lag 1 has a larger coefficient than lag 2, has a larger coefficient than lag 3, right? So they decrease progressively. So we're seeing that, what's really important in determining or predicting the dependent variable in the current year is just the value of the explanatory variable in the current year. Okay, what is the difference between impact propensity and long-run propensity? So impact propensity is the immediate effect. So just think of impact, right? What is going to happen right now? Impact, someone punches you. It's got a direct impact on you, right? Long-run propensity, right? So, if I punch you really hard in the head today and tomorrow and the day after that and the day after that, maybe in 10 years you get, brain damage. So there's long-run propensity, whereas in, impact propensity, I punch you, you get hurt right now. So impact propensity is the immediate effect of a change in an independent variable on a dependent variable within this time series framework. Okay, so how much the dependent variable will change as a result of a 1 unit change in the independent variable at a specific point in time. Long-run propensity, that refers to the cumulative effect of changes in the independent variable on the dependent variable over time. So it considers both immediate and delayed impacts of the independent variable on the dependent variable. So again, think back to like someone who boxes, right? The long run propensity of boxing is that you get brain damage because we're taking both the immediate, so you're getting punched right now, and the delayed impacts, all the punches you took in the past, and how that affects your health, let's say, is a dependent variable. Okay. So here they just want you to reiterate the 6 key assumptions that we make. So linearity, no serial correlation or no autocorrelation between error terms. So error terms are independent of each other. Okay. There's homoscedasticity, right? So that is, again, it's not that your error terms are gay. It's that the variance of the error terms is constant across all levels of the independent variables. Okay. So basically, the conditional variance stays constant regardless of your explanatory variables, that your error terms are normally distributed, that there's no perfect linear relationship among the independent variables, and this exogeneity, specifically strict exogeneity, that the independent variables are not correlated with the error term, right, over time. So for all independent variables over all of time. That's for strict exogeneity. And then just a note here on exogeneity, you get just like standard exogeneity and strict exogeneity. So when you say just exogeneity, that just means that the independent variables are not correlated with the error term in year t. but maybe the independent variables of year t minus 1, t minus 2, t minus 3, etc. could potentially be correlated. So when you allow for potentially the independent variables of previous years, of lagged years, to correlate with the error term, you just have exogeneity. When you have strict exogeneity, it means that for all independent variables over all time, there's no correlation with the error term. Okay, so consider this. What does alpha 1 greater than 0 and alpha 1 less than 0 imply about the behavior of the dependent variable in year t over time? So again, this is why the theory is so important. So obviously, if alpha 1 is greater than 0, yt increases over time, so that's a positive trend, and alpha 1 less than 0 decreases over time, it's a negative trend, right? So as time increases, the expected value of yt falls, or if it's a positive trend, as t increases, the expected value of yt rises. Again, they like this example. So in this model, you have all those things where the growth rate, or a GFR, is the fertility rate. Pull is a dummy variable. How does the availability of the pull impact the fertility rate compared to periods without access? Okay, so here's how I interpret it. So the negative coefficient of negative 31.59 indicates that the availability of the contraceptive pill is associated with a decrease in the fertility rate by approximately 31.59 units, compared to periods without access to contraceptive pills, all else being equal. Or, if you speak Latin, you can say ceteris paribus. 2.23, consider the following housing investment model, and here's the regression output, okay? And so they show you that some of these coefficients are statistically significant and some of them are not. Right. So now they say, would you conclude that there is a relationship between the log of investment per capita and the log of price? Justify your answer by conducting a proper analysis. So 5 easy marks. So the initial regression without the time trend shows a strong statistically significant between the log. So you'll see here, if I can show it over here, this is the model without trend. So that's not included. So time is not included as an explanatory variable. And then here, model with trend, here we go. Okay, and so this is statistically significant. Now in this one over here, our constant was statistically significant and the log price, that coefficient, was statistically significant. But now we add in the trend and look here. Not only does the sign of price, the coefficient, change, but also it's no longer statistically significant, right? Because the standard error, so if you use a 0.381 over 0.6790, you'll get a t-value of like 0.5. So you'll get a pretty bad t-value. You'll get a p-value that's much more than 0.05. Then they like to mention this thing about people with a taste for life, right? Spurious regression problem, right? So when you think about spurious, just to remember it, so spurious, maybe think about a friend who went to Spur, who was a fake-ass bitch, and so spurious means fake. Cool. So when a time trend is included, the coefficient becomes insignificant, so it suggests that the earlier relationship was misleading or spurious, right? This time trend corrects the spurious regression issue, so it indicates that housing investment is influenced more by time than by price. Cool. Now, many economic time series are better approximated by an exponential trend, which suggests that the series exhibits a constant percentage growth rate over time. Write down a linear economic model that represents a time series y of t as an exponential trend. So insanely simple. So you'd say log of y of t equals beta 0 plus beta 1t plus mu of t. Again, this is an exponential trend. So remember, with the linear trend, you don't have a log. It would just be yt equals beta 0 plus beta 1t plus error term t in year t. But now with an exponential trend or exponential model, whatever, you just log the dependent variable. And so then you just interpret it. And so beta 1 or alpha 1 is the coefficient that represents the constant growth rate of the series. And the error term is the mu t is the error term capturing any deviations from the model. Okay. And so consider log of year t equals 2.2 plus 0.027. Interpret the coefficient of t in terms of a change in yt. So the coefficient of 0.027 suggests that the dependent variable in year t grows about 2.74% for every 1 unit increase in t or time. Okay, pretty simple. What is serial correlation? Serial correlation, again, these are now from the exam, so you'll see the questions get repeated. Serial correlation, also known as autocorrelation, is a correlation of a time series with its own past values. Alternatively, serial correlation occurs when the residuals or errors are correlated across time period, violating the assumption of independence. And then 3.17, under the first to the fifth assumptions, what do we conclude about the distribution of the OLS estimators, right? So the OLS estimate, I'm not sure if this is correct, because I think the TS6 is our... Oh yeah, so if TS1 to TS5 are satisfied, that implies that TS6 is also satisfied. So that means that the OLS estimators are asymptotically normally distributed. And so these usual, standard areas, T-stats, F-stats, LM-stats are asymptotically valid. So we can conduct statistical inference. Explain what is meant by time series data. I have done that in the theory, but again, data collected on the same observational unit at multiple points in time, right? Sorry. Cross-sectional data is data collected on multiple observational units at a single point in time. The data is a snapshot and the order of observations is arbitrary. So the income of 1,000 individuals in 2020. Whereas with time series, it's data collected on the same observational unit, so a country, a company, at multiple points in time. So it has a natural temporal ordering. And so the main difference is temporal ordering, and obviously that they are they the same observational unit or multiple observational units. And then here again, define what is meant by trend, cycle, and seasonality. We've already done that. State 3 reasons why it is important to understand the components referred to in questions 4.2 in the time series analysis. So we've already done that. I think that's correct. This question might be a bit wrong, but definitely accurate forecasting. Answer: the accurate forecasting and avoiding spurious regression is correct, but the policy formulation one is a bit dodgy, so I wouldn't use that one. I would use the previous answer. Compare and contrast a static model and an infinite distributed lag model in econometrics. And yes, we've already done this. A static model, effect of x on y is immediate and confined to the same periods. Infinite distributed lag model allows the effect of x on y to be distributed over an infinite number of past period, with the impact diminishing over time, right? So the difference is the time dimension of the effect, wada. Suppose you have the following bivariate time series regression model. Literally, we've had this problem before, so it violates the strict exogeneity assumption. So we could have potential limited variable bias or feedback from the dependent variable y, which is in the error term, to future values of the independent variable x. How would we modify it? Include a lag of the independent variable, and then there's the modified model. So nothing crazy. 4.6, assume we have a time series model of the following form. There's the form, express the cumulative effect or the long run propensity associated with this model. Again, you just sum up the coefficients and then explain the concept of homoscedasticity in the context of time series analysis. So that means that the variance of the term u in year t is constant over time and does not depend on the values of the independent variables. So formally, the variance of the error term in year 2 given x, so x is again a matrix of the explanatory variables, so all explanatory variables across all of time, right? The variance of error term in year t depending on x is equal to whatever thingy squared, standard deviation squared for all t. So it's equal to a constant variance and the true population variance. And then what are regime changes? I don't know if it'll be tested, but let's just chat about it. So regime changes are structural breaks where the underlying parameters of an economic model, like the intercept, slopes, or error variance, change at a specific point of time. How does this violate homoscedasticity? So a regime change can lead to a change in the volatility of the economy. So the variance of the error term is different in one region compared to another, violating the homoscedasticity assumption. And so here they give you an example, or DeepSeek gives us an example of the Great Moderation. So from the 1980s to 2007, economically in the world, things were pretty much people were chilling. And then, as well, people in America were chilling. Some of us were, there was apartheid in some places. But anyway, then we had the global financial crisis in 2008, 2009. And then after that, things were kind of not so nice. And so obviously what that means is that the variance changes, right? So initially the variance is quite low. There's not a lot of variance in the time series in terms of economic growth. But then later, there's much greater levels of economic volatility. Right, so a single regression spanning both periods would have non-constant error variance because, from, let's say 1980 to 2008, you would have a specific variance, and then 2008 onwards, you would have a different variance. So that's heteroscedasticity. And I believe, I thought we were at the end, not quite, sorry. So given that the expected value of yt minus 1 equals alpha 1, specify a model that includes a time trend and explain each component of the model. So there's the thingy key, and then you can just explain it. So yt, the value of the dependent variable at time t, beta naught, the intercept representing the expected value of yt when t equals 0, beta 1, the coefficient on the time trend, so it represents the expected change in yt for one period increase. So given the condition e of yt minus 1 equals alpha 1, it follows that beta 1 equals alpha 1, or you could just use alpha 1 instead of beta 1 in the model. And then error ut, the error term capturing random deviations from the trend. So this is a linear trend model with a variable yt is expected to increase if beta 1 greater than 0 or decrease if beta 1 less than 0 by a constant amount each period, right? It's a linear because the yt is not logged. What is a stochastic process in a time series and what is its significance? We've already done that. So random variables, ordered in time, Vito's realization of random variable, significance, theoretical, we don't need that. We've already done it. State 3 reasons why it's important to understand the components of trend, cycle, and seasonality in time series analysis. We've already done that. Compare and contrast a static model and infinite distributed model. We've already done that. But yeah, just quickly pause. You can have a look at it if you want. That DeepSeek told us. You can also look at the previous answer. But yeah, we have done this. But this is just to show you, these are questions from the preview questions from an exam and from a test that they like to repeat questions. Okay, again, you have this thing and then you have error term correlated with the past values. It's literally word for word the same question, right? You solve it in the same way. It violates strict exogeneity. There's omitted variable bias. You include a lag, and then you have the modified value model over there. And then here we go, using a variable such as the monthly sales of a commodity. Intuitively explain what a serial correlation is in the context of time series data. So that means that the random shock affecting sales in one month is correlated with the shocks in previous months. And this now, for example, this answer is about the error term, right? However, so when I plug this into DeepSeek or the AI or whatever, they were like, a serial correlation only has to do with errors, but remember it also has to do with the value of the explanatory variable. So the previous explanation that we had is basically just to say that the value of sales in 1 year is correlated with the value of sales in the previous year or in a different year. So assume we have a time series model with this thing, the cumulative effect or the long run propensity associated with the model, boom, add up beta 1, beta 2, beta 3, beta 4, there we go. Woo, my word, my God. There's a lot of questions. Many economic time series are better approximated by an exponential trend. Write down a linear economic model that represents a time series yt as an exponential trend. So all we need to do is we use a log or ln, natural log of yt equals alpha naught plus alpha 1 times t plus error t, where alpha 1 times 100 is the approximate constant percentage growth rate per period. And there we go, guys. We are done with all of this stuff. So what I would say is, if you stayed this long, thank you. Please like the video, comment, subscribe, all that stuff. And then also, I did all of this for free. Like, I 100% totally did it for free. It is literally, what is the time now? Well, let me check what the time is. It is 3:25 a.m. right now. Okay, so yeah, I hope you guys enjoyed the video. It helped me with my revision. I'll use these videos for my own revision for the test. And then also, if you would like to, if you are like balling, you don't know what to do with your money, it's like falling out of your pockets on campus and it's super embarrassing, your parents are super rich, I do have a link in my on my channel for Buy Me a Coffee, so you guys know how expensive Food and Connect is. So if you want to sponsor me a coffee, you can do that, send me a message, whatever, and just be like, yo bro, thank you, you're so goated, thank you for saving my life, and thank you for making sure that I pass the test and don't disappoint my parents and don't lose my NSFAS and all that stuff. So if you'd like to, you can do that. You really don't have to. I'm just making this because I enjoy it, because it gets me to practice my YouTube skills, and because it's good revision for myself. So I hope you guys enjoyed it. Remember, like, comment, subscribe, all that general stuff that YouTubers say, and good luck for the test.
What can I say except you're welcome?